Hello everyone, my name is Camila Alvarenga. I'm a master's student at the University of Alberta, and I'm here today to present a study I have been developing with the help of Dr. Abdulrazak under the supervision of Dr. Michael Hendry. This study regards the moisture monitoring of a railway embankment and the effect of a wicking geotextile. So the main objective of our study is to check whether the wicking geotextile improves the drainage and the strength of the foundation soil, and the minor objectives set consist of monitoring the embankment moisture content by using 5T sensors and the Diviner 2000. Then the collected data was used in a model that quantified the influence of precipitation on the soil moisture. We also needed to understand how the embankment soils would behave under moisture changes. For that, we decided to characterize the soils by performing a series of tests. And our last objective consisted of using these characterization tests performed to identify the effect of the insertion of the geotextile on the unsaturated soil strength by performing a direct comparison between the remediated and the control section. To meet our first research objective, a track section kindly conceded by CP was instrumented aiming the collection of moisture data, and the instrumented track section is located at the milepost 153.8 on CP's Scotford Subdivision, that is represented by a red pin in Figure 1. The site made possible for us to assess seasonal changes of moisture content within a clay subgrade at an area where clay pumping and settlement occurred due to drainage issues. To solve these mentioned problems, CP decided to remediate the embankment by using two geotextiles. And the geotextiles used were Mirafi RS 580i, a woven geotextile that was placed between the ballast-subballast for separation and reinforcement purposes. And the other geotextile is Mirafi H2RI, a wicking geotextile that was positioned between the subballast subgrade interface and has the goal of facilitating the diversion of water from the track embankment to the side ditches. The principle of this wicking geotextile is that the wicking fibers stimulate an equilibrium between the suction values seen for the geotextile and the soil. Therefore, the geotextile will constantly remove water from the soil until it reaches the water content related to the suction value of equilibrium, which can depend on the environment and can go up to 100,000 kPa. We worked on several versions of the instrumentation plan to ensure it was aligned with the contractor's work plan and timeline for the track construction, which had a time limitation of 2 days to minimize the impact on the demanded traffic. This figure here illustrates the configuration of the moisture sensors and the access tubes installed at our remediated section in the final plan. As you can see, the access tubes that was used for the moisture profile readings go down to the subgrade, but for the sensors, they only go down to the subballast. These sensors, TG4 and TG5, they were installed during the reconstruction, so we don't have access tubes associated with them. So the instrumented control and remediated sections of our study are adjacent, as shown in Figure 3, what allowed us to evaluate the effectiveness of the chosen remediation more effectively, since most of the site conditions should be similar for both parts. A total of 10 access tubes were installed at both sections for measurements. At each section, the tubes installed at the northern side of the shoulder, over here, go down to the subballast, while from the 3 in the center line, 2 go down to the subgrade, over here and over here. And the third one goes down to the subballast also. So T3 and TG3 only go down to the subballast. And 2 moisture sensors here called TG4 and TG5 were the ones that were installed in the subgrade simultaneously to the excavation, and that's why they don't have access tubes associated with them. And the blue circles over here were used for the moisture profile readings, and they go down to the subgrade. Now we're going to discuss the sensors used in the instrumentation plan for moisture monitoring. The Diviner 2000 is a portable soil moisture probe that obtains moisture readings throughout the soil profile at 10 centimeters intervals up to a depth of 1.6 meters. And the 5T sensors allow the determination of water content, soil temperature, and electric conductivity of a certain location of the soil, and is connected to a data logger that takes readings at specified times. Our work for the installation of moisture sensors and access tubes was extremely hard because we had to work around the construction equipment, having only 2 days to complete our instrumentation setup. And the rehabilitation started with the excavation of 55 centimeters of embankment down to the subgrade layer, and 2 moisture sensors were then installed at the excavated subgrade and protected by electrical conduits to avoid damage to the sensor wires before we could continue with the construction. After the sensors were placed, the Wicking Geotextile was then laid at the top of the subgrade and clean subballast material was poured. The reinforcing geotextile was placed over the subballast and clean ballast material was placed on the embankment. This ballast material was then submitted to tamping and leveling. On the second day, we needed to install 10 access tubes on the embankment simultaneously to the track reconstruction, what made it extra challenging for us. The ballast was very difficult to go through, so it was necessary to dig a trench down to the bottom of the ballast before using an auger and a hammer to push the PVC tubes to the desired depths. This picture here shows the final setup at the end of the construction, with 4 access tubes installed at the remediated and 6 access tubes installed at the control section. After the construction, we went back to the site and installed the remaining 5T sensors, protecting them with electrical conduits to avoid damage to the wires. 2 data loggers were also set up to collect data from the 5T sensors at a 12-hour interval, one at the control and one at the remediated section. We are still going to the site monthly to collect the data for our analysis, even during the winter when the truck cannot move through the deep snow and we have to walk from the closest roadway to get to our site. When we collected the data loggers information, we also collected the continuous moisture profile by using the Diviner probe, and this was also done monthly. And these readings are very important to view how the moisture is changing at different depths of the embankment. Here you see the raw data used for our model, which consisted of volumetric water content values and precipitation data. The precipitation data seen here was obtained from nearby weather stations at the Environment Canada website. And the green boxes in the graph were defined by the temperature of the subgrade soil. At this period, soil temperatures stayed below 1 degree Celsius, and we are not sure of how the sensors would measure frozen water. Therefore, the data from this period was not used in our analysis. And these are the readings we have from the Diviner probe versus the readings from the 5T sensors. We see a similar trend for both sensors for the subballast, with the remediated section displaying higher moisture content for the subballast layer. However, the subgrade trend for the top part of the layer differs from what is seen for the 5T sensors at a lower depth. We are currently performing an analysis to find out how the differences between the readings are related to the equipment default calibration. Due to the suspension of field research activities caused by the current situation, moisture profile readings were not collected by the Diviner from May to August. Therefore, we will continue monitoring the moisture during the next year to be able to understand the meaning of these readings. To accomplish the second objective, which was to quantify the degree of correlation of the moisture of the embankment with precipitation, we used a model called Antecedent Precipitation that can relate moisture changes with the amount of precipitation occurring during a certain day range. The control site moisture data is represented in black, while the remediated section data is represented in red over here. The takeaway from the antecedent precipitation graph is that we can see how the antecedent precipitation and volumetric water content values are related. The model has shown that the sensor at the subgrade of the control section is strongly correlated with precipitation. As you can see, when we have a higher amount of precipitation, we see higher moistures associated with it. While the remediated section does not show great changes in moisture, even with the occurrence of higher amounts of precipitation, what can be seen by the flat curve over here. That means that the Wicking Geotextile seems to be decoupling the precipitation from the subgrade moisture content. However, we still need to rule out the effects of the reconstruction. In order to accomplish the third research objective, which is to identify how the embankment and subgrade soil respond to moisture changes, we performed a series of tests described here. And we also performed the direct shear tests for the subballast and subgrade materials to measure the saturated shear strength parameters of these soils. The results are going to be used to analyze the impact of the geotextile on the soil strength. So the relationship between the soil water content and soil suction is defined by the soil water characteristic curve. They are widely used for the estimation of unsaturated property functions and are related to permeability and strength parameters. We performed SWCC tests for around 10 months to determine how the changes in moisture content would translate to soil suction values. These tests take a long time, and the COVID measures made us take even more time to perform them due to lab closures occurring during these times. We then used the volumetric water content results of the subgrade of both sections for a comparison of metric suction by using the SWCC curve shown in the last slide. In the saturated soils, the coexistence of water and air results in negative pore pressure, also called a soil suction, which increases the effective strength of the soil. So the higher the soil suction, the higher the unsaturated strength of the material is expected to be. So here we can see greater suction values at the remediated site for the most part of the study, leading us to believe that the strength could be improved due to the inclusion of the Wicking geotextile. However, lately, slightly higher suction values are seen at the control section, and the situation will be monitored for the next months to check whether the geotextile effect has a short lifespan or if it is only a momentary difference due to the decrease in temperature of the soil caused by the drop in the air temperature. So the conclusions are that for the control section, the moisture changes have shown to be strongly correlated with precipitation in 2020, while for the remediated section, no significant changes were seen in the moisture throughout the entire study. And these results may indicate that the Wicking geotextile could be decoupling the subgrade moisture values from precipitation events due to water interception. Regarding the suction values and the soil strength, the remediated section has shown constant values of suction until October 2020, with slight changes after this period. Then what we see is higher values of suction associated with the remediated section up to mid-September 2020. Then the control section starts presenting higher values of suction after September. And the situation will be monitored during the next spring and summer to check if this trend is only momentary due to the decrease in temperature of the soil caused by the drop in the air temperature, or if the geotextile has a limited serviceability. So the upcoming plans for the study consist of estimating the in-situ unsaturated shear strength for both sections at the subgrade layer by using the volumetric water content values from the field measurements, the soil water characteristic curve, and direct shear test results. We'll also recalibrate the Diviner probe specifically for the soils found at the field to correlate with the results found for the 5T sensors. And we'll track the long-term effect of the geotextile on the subgrade moisture and check whether the temperature cooling has caused the control section to have a decrease in its moisture on the last months. Finally, it is also in the plans to perform large-scale laboratory tests and/or develop a numerical model to evaluate the geotextile mechanism and quantify its impact. I would like to thank CP for considering us the site, Kelvin Sadler for helping us with the data logger setup, and Daniel Wong from CP especially, but there's also a lot of people to thank here. Thank you everyone for being here. I'm ready for any questions you might have.